All right. Hello, everyone. This is Volts for September 17th, 2025. Are we finally getting 3D printed batteries? I'm your host, David Roberts. As Volts listeners know, batteries rule. They help everything and everyone on the grid. Few things would be more helpful in accelerating the energy transition than making it easier, cheaper, and faster to manufacture good batteries. The main working parts of batteries are the electrodes, the anodes and cathodes, and there are, roughly speaking, two ways to manufacture electrodes: wet and dry. The wet process, which is overwhelmingly the most common today, is a bit like inkjet printing. The active materials that will compose the electrodes, particles of nickel, magnesium, iron, what have you, are mixed with solvents into a liquid slurry, which is then sprayed onto a thin foil substrate by a tiny nozzle. The foil must then be dried in large ovens. The solvents evaporate and are recaptured, while the active materials bond to the foil. It is a somewhat complicated and expensive process, but it is well understood, running at enormous scale, and producing high-quality results. The dry process is more like laser printing. It does not use solvents and thus involves no liquids. Instead, the active materials are mixed and then deposited directly onto the foil, where they are compacted into a uniform layer and bonded via heat and pressure. In theory, the benefits of the dry process are obvious. You get rid of solvents, which are often toxic and carbon intensive. You get rid of ovens, which are large, capital-intensive, and energy-hungry. You reduce waste, simplify manufacturing, shrink your physical footprint, and reduce your environmental footprint. What is not to like? In practice, however, it has proven much more difficult than expected and taken much longer than expected to push the dry process to anywhere near the speed and quality control of the wet kind, outside of lab conditions. Now, a company called Sakuu claims it has cracked the code. It is selling a manufacturing platform based on dry printing electrodes. Giant 3D printers, basically, which the company says can produce electrodes of almost any chemistry rapidly and in high volume. I am extremely excited today to be talking to Sakuu's CTO Karl Littau, a scientist who has been working with and around materials sustainability for more than 30 years. We are going to discuss how Sakuu has overcome the challenges of dry printing, what its platform can produce, and what it might be able to do in the future that the wet process cannot. All right then, with no further ado, with that rather extended introduction out of the way, Karl Littau, welcome to Volts. Thank you so much for coming.
Thank you for having me, David. It's a pleasure to be here.
I briefly talked about the wet process there. Is there anything you think I missed? Is that mostly what you think people need to know about it, basically? You spray the stuff on the foil, you dry it in ovens. Are there additional details that people need to know?
No, I think you really covered it. It is a very simple process, actually. I mean, it's a lot like frosting a cake. You take a slurry and you basically slather it on. You do want to make sure it's as uniform as possible. Batteries don't like things that are non-uniform, that are really irregular. So it has a lot of crazy solvents in it, which are not great for the environment, and they do take a lot of energy to remove. And so that's been the headache of a lot of people who work in battery manufacturing. If they could make that process as easy as a laser printer, I like your analogy a lot, then it would be so much better, a much smaller, a lot less energy consumed, and a lot less headaches for the people in manufacturing, and ultimately a cheaper battery.
Yes, but people have been banging their head on this wall for a good while now, right? I mean, I feel like the first hype I heard about this possibility was like 10 years ago. So is it fair to say that it was more difficult than people thought it would be?
Yes, it is. And also, the simple process that people do with wet is very mature and it works and it's well understood.
Right.
Any new process into an industry like battery manufacturing is always going to have a very high bar for performance. It has to meet or exceed the reliability and the productivity of the current process before people are going to put it into place. And anytime you change from wet to dry, it's a very fundamental change in manufacturing. There are always going to be some manufacturing challenges that have to be overcome. And some of those took a little longer to work out. But I think we're right at the point now where people are seeing the advantages. They're becoming more satisfied that the processes and the materials and the manufacturing equipment can be as productive or more and as reliable or more reliable than what's in place now. And so I think we're going to start seeing people evaluating this at first at pilot scale and then scaling up to mass production.
But just so people can wrap their heads around what the 3D printing process is, it's dry, which means you just have particles and you're putting them directly on the foil and then they are compacted. What does that mean exactly? Is it like a little roller like you have in your in your kitchen, like you roll out a pastry with? Like what compacts the particles onto the foil?
Exactly. It's a lot like a laminator. I mean, a
Mm,
lot of people have experience with laminators for making like I don't know, badges or cards and things like that. Very similar. Laminators use heat and pressure in order to compact it and activate some kind of adhesive binder that holds the card together. And that's actually also in a laser printer. Laser printers do the same thing. They all have a fuser in it where the toner, everybody's familiar with toner. It's all messy and flows, it gets everywhere. But in the laser printer, there's two steps. One is to pattern the toner, and then another one is the fuser that uses heat and pressure to stick it to the paper.
right.
The dry process for battery manufacturing is the same. It just uses heat and pressure in order to get the loose powder into a compact and cohesive and adhesive, meaning it sticks together, electrode that can go into the battery.
As I understand it, there are sort of like two big challenges sort of emerged from that description. One is getting these active ingredients right, getting your whatever the recipe of the dry material that you're putting in just right. And by the way, perhaps I'm taking the printer analogy too seriously, but when you put these dry materials into the 3D printer, is it like a bucket, a tray? Are you sliding? Just to give us a visual sense, like where do you put the raw materials into the 3D printer?
It is a lot like a laser. It's not a bad analogy, right? So there is something like a cartridge
Right.
that holds the dry powder. And then it dispenses that dry powder onto a moving, what they call a web. It's basically a roll of material that will eventually go into the battery. And it's continuously dispensing the powder onto the web. And the system then has a second step that uses a smoother to make it uniform, very uniform
And
layer.
that's the trick, right? Like that's the main trick is you need a perfectly uniform layer of this stuff. And as I understand it, part of the challenge over the past decade has been trying to do this, without any liquids, trying to make them adhere to one another and to the foil. They tend to sort of dry and crack or things like that. Like that's the problem that engineers have been fighting through to get that perfectly uniform layer, right?
That's right, exactly. And not only that, but ultimately at the end, it has to work in the battery. And the battery manufacturers won't tolerate any reduction in performance. So the dry process has to meet or exceed the performance of the wet. And To do that has been the challenge. And you're right, half of the battle is on the equipment to make the material uniform, to activate the binders with the fuser, the heat and pressure, and to get it to stick together and work in the cell. The other half of it is what happens before. So the formulation of that dry powder is super important. It's not as simple as just taking the few ingredients, putting them in a blender and turning it on.
So it's not like you take the same mix and just take the solvents out.
No, no, exactly.
Right. You have to reformulate the.
That's right. That's right. It really is like a toner. It's highly engineered, where you put these materials together in a particular way with a particular process and a particular piece of equipment, balancing how they're mixed together. But then even on the microscopic level, the ingredients in the battery are combined together to work very, very well in the printer and then very, very well in the battery.
Got it. Part of the promise here is that these 3D printers could print different kinds of chemistries. And that's just a different recipe of dry materials. One of my central questions here is, which I couldn't quite wrap my head around from reading the materials, is one of these 3D printers sort of, Catholic? Like can the same printer print batteries of different chemistries? Do you know what I mean? Like, is it just a matter of reprogramming the same machine, or are you building 3D printers? Are they custom designed for particular chemistries?
Yeah, that's a great question. Nobody in manufacturing likes to have equipment that is dedicated to just one product,
Yes.
right? They want to be able to print, their entire product suite on the platform. And that's our goal too. And so, yes, we are able to print multiple materials on the same platform. And to do that is in the upfront formulation, right? In actually making the dry printable material. We work very hard on all of those processes. And when we are successful, we are able to make powders, one for different chemistries of battery, different flavors of lithium ion batteries that can be printed on the same material. Now, the recipe on the platform, on the printer, might be a little bit different, but the hardware is the same. We were able to use the same thing.
Just so I'm sure I'm getting this, I have one of these 3D printers, and right now I have it making, I don't know, NMC, nickel, magnesium, cobalt, sort of traditional high energy density batteries used in high-end EVs. And I want to, for whatever reason, stop making NMC batteries and start making LFP batteries, let's say, lithium iron phosphate batteries. All I have to do is replace that tray full of one set of dry materials with a tray full of different dry materials. Is that the only, do I have to reprogram it? What exactly is involved in taking this machine that's doing the one thing and making it do the other thing?
Yeah, that's essentially right. Now, there may be a small change in terms of the process parameters on the printer. The certain elements of it might run a little faster, a little slower, different things like that in order to actually see the same performance. But yes, it's the same printer.
That's amazing. So you buy one of these machines, and technically, if you buy one of these machines, you have bought the ability to print any extant battery chemistry. Are there any chemistries that are off the table for any reason? Because I thought one of the early critiques of 3D printers is that they were unable to use some of the materials that you could use with solvents. Are there any limits on the range of chemistries that you can get out of one of these things?
I mean, there is always going to be some restriction at some point, but anything that can be formulated into a dry powder, our system can print. Now, it uses heat and pressure to activate the binder. That uses a property of a binder called thermoplastic, meaning when you heat it up, it gets soft and then starts to get sticky. Some binders don't have that property, that they're more of a just adhesive as they come, right? And so they don't get sticky when they get heated. And so certain binders don't work as well in a system like this, but any adhesive that can have that thermoplastic property can be used. Now, there is an advantage of dry. It actually can use a lot of binders that wet can't use. For example, polyolefins, simple polymers like what we use in like plastic wraps or bags or trash bags. I mean, polyethylene or polypropylene. There are no really good solvent systems for those, and so you don't see them being used in batteries very much. However, a dry process could use those. They're cheaper. They potentially can actually make better batteries. And so there's a lot of possibility that dry printing, 3D printing can open up.
So theoretically, I buy one of these machines, and not only am I buying theoretically the ability to print almost any kind of battery, in a sense, I'm future proofing myself as well, right? Because I could theoretically print future battery chemistries that that we haven't even developed yet. So, what about speed? My understanding also is that one of the big dings on 3D printing in the past is that it just doesn't have the throughput. It just doesn't go fast enough to keep up with the wet process. Where does that stand? What's the speed comparison?
Actually, speed, I think, ultimately is not going to be a problem. Now, whenever a new technology is introduced, there's always a learning curve in order to improve the performance and throughput, the productivity of the tool. And right now, the dry process is on that learning curve. And so it started very slow. Typically, we measure it in meters per minute, right? Like a high production system today that uses the wet process can operate 50 meters per minute, even higher. The dry processes started pretty slow.
Like a lot of people have seen these sort of desktop 3D printers at work, and they're amazing, but they're slow.
Right. But let me go back to the analogy of the laser printer. The laser printer, in a way, is a 3D printer. It just does one layer.
One dimension.
Right. But it's incredibly fast. Production laser printers can run at 100 square meters per minute, which is as fast or faster than production battery coaters today. So there's no inherent limit in terms of that. But the technology has to be optimized for the application. Most people's desktop 3D printers, the things they have at home, these are essentially anything printers, right? Anything that you can make a design, you can print it, right? To do that, a lot of trade-off has been made in terms of speed.
Oh, I see. So if they were just designed to print one kind of thing, they could theoretically go much faster.
That's correct. You're right. The Sakuu printers, our brand name is Cavion. Our Cavion printers that we use for electrode fabrication for batteries, it can't make a widget. It can't make a part.
Right,
it's not
right.
designed to. It makes a battery electrode, which is a two-dimensional thing, and it does it very fast. And typically, the batteries are rectangular. Sometimes they're rectangular. Their cylindrical ones are essentially rectangular that are rolled up into a cylinder. And so that's what it does. It does that really fast. It puts down the powder and activates it and makes electrodes.
So this gets to another question a lot of people had. These 3D printers are only printing electrodes. They're not producing batteries. In other words, they're not printing the casing and all the other bits. Is it just the electrodes that these things are producing?
That's right. Yeah, that's the real need right now. That's the only wet step in the fabrication process right now for batteries. And that's the one that gives the battery manufacturers the biggest headaches.
Like manufacturing of the other parts is already good.
Right. They're much less of a problem today. However, once the shift for dry processing is happening, then the headache moves to another part of the process. Sakuu, we have actually printed every piece of the battery. So the current collectors, the electrodes, of course, the separators, we have printed everything. All of that can be printed through a dry process.
Interesting.
But we're focusing on the electrode right now because that's where the biggest market is, and that's what we're addressing. But the vision of being able to print the entire battery in a single system, that can be realized.
Wild. Can you help us envision the scale of these things? So, like, how small can they get and how big can they get? Like, what is the smallest size of printer that I could buy from you? Like, could I put one in my garage, or are they container sized? What's the sort of scale here?
I mean, they could go in a garage, I think. They can be smaller than a vehicle.
Really?
Yeah, they can be because they're very simple, right? There's just a front end which does the powder preparation, deposition and preparation, and then a calendar, we call it, where it applies the heat and pressure. That's the laminator we were talking about before. Those are not particularly large. There's also web handling, winders and unwinders, but they can be fairly compact.
Interesting. So you could, in theory, like be printing electrodes in your backyard if you wanted to be like a real DIY type of person. I guess you'd need to get the dry materials from somewhere. You probably couldn't do that in your garage.
Yeah, I wouldn't recommend that.
Yeah, so these are small and pretty modular, and then you can just the idea for manufacturing at scale is the idea to make the printers bigger, or is the idea to just stack up a bunch of printers? Are the printers a standard size?
So that is our goal, is to make systems that are a single size. We get the economies of scale. It's always good in manufacturing facilities to have multiple units of the same equipment, because that way, in case something goes down, you still have capability. You don't want to put all of your manufacturing eggs in one basket.
One point of failure.
Exactly. Now, the wet process, there's an economy of scale that drives the industry to making very, very large systems. It's because of the drying. Dryers tend not to shrink very well. When they get small, then the heat loss becomes a problem. So they like to be big. And so a manufacturing facility may only have 2 or 3 wet coaters. Doing it dry changes the calculus. The economics of it actually favors smaller systems and more of them in order to have the redundancy and also the compact size, easier to be serviced, and also scalable, because you can start small and then scale up by adding more printers.
Right, like Legos. And, it's a consistent theme of this podcast is if you're producing the same thing over and over again, you get that learning curve. You get that learning by doing. That's the easiest way to bring down costs, is to replicate the process over and over again.
Right.
So when you're selling this to people, I mean, as we mentioned at the beginning, the shift from wet to dry is pretty fundamental. So if you're going to a battery manufacturer, you're not pitching like, we have a way to upgrade your current system. You're pitching a replacement system, basically. Is that right? Like this would be like replacing one system with another, not. So I wonder, like, are you only selling these to people who are building new plants, or is anyone talking about replacing wet facilities with dry facilities?
It's both. So current manufacturing facilities are sometimes interested in upgrading to dry. And so the system is designed to be a drop-in replacement for the manufacturing today. More common is a new facility. The battery industry is growing quite dramatically worldwide, and so more opportunities are there for introducing new technology in an entirely new facility.
Okay, so let's briefly go through the sort of benefits you're pitching to customers. We sort of touched on them, a couple of them, but I just want to put them all in one place. One is the elimination of the solvents and the water. It says you've eliminated water. Is that, when you say dry, is there no water involved anywhere here? Is this like a water-free? Because water is a big choke point for a lot of manufacturing.
Yes, there's always water in manufacturing facilities, usually for cooling. That still happens. And so in heat exchangers and things like that, we'll have water cooling. Water is not good for lithium-ion batteries. So usually if there is water somewhere in the process, there's another step after that in order to get rid of it. And so many of the wet processes do use water in current manufacturing. When you shift to dry, those are all eliminated.
Right. And you say this, relative to the wet processes, reduces CO2 emissions by 55%.
Mhm.
Is that from the solvents, or is that from the energy running the ovens, or both?
It is both. The biggest component is the energy consumption. There's 2 parts of that, especially for the toxic solvents. It takes a lot of energy to dry. And so they have these ovens that are on all the time and putting out a lot of heat. The second is that the solvent, when it dries off of the electrodes, you can't just run it out the stack and the building, right? There is a solvent recovery system that has to be used. And that's essentially a condenser. And so it uses a lot of energy in the compressors and such to chill what they call the effluent, the gases that come off, to get all the solvent out before they can exhaust it. Those are both really energy intensive processes, and switching to dry gets rid of both of those.
Got it. So those CO2 emission reductions are basically just a function of the energy consumption reductions.
There's a few other areas that does save, but by far the majority is energy consumption.
Got it. And you say 60% smaller physical footprint, floor space for manufacturing. I'm assuming that is mostly getting rid of the ovens?
That's right.
Because those ovens, as you say, are big. And I bet probably also the most unpleasant part of any manufacturing facility. And then 20% reduction in capital equipment costs. That's just to say it's cheaper to buy one of these printers than it is to buy the component parts of the wet process, basically.
That's right.
And 56% savings in utility operating costs. What is that as distinct from the energy consumption?
I think it's easiest to think about them as one and the same.
Got it. So you're promising people you don't have to mess with solvents, you don't need a bunch of water, lower CO2 emissions, lower physical space, lower cost in a variety of ways. Are you selling these now? Is one of these out in the field doing its thing, or are they all in sort of pilot testing? Where are you business-wise?
We are taking orders for them. We are in the evaluation phase. So our customers are coming to us and evaluating their materials on our tools with the processes that we develop. And so they've been doing that evaluation for some time now. And as I said, we're just getting our orders. The first systems are going to go into their laboratory or pilot production facilities. And so this next year is when we're going to start seeing those shipments and this data starting to come out from our customers' facilities.
So you're shipping basically like test units this year. Customers will start using them, figuring out whether they work, getting real field data. So we don't have one of these in the field producing electrodes.
Not yet, no.
We hinted at this earlier, but there's a couple of ways in which, in theory, dry produced electrodes are better than wet produced ones, have advantages. One of these, as you sort of alluded to, is, at least it's what's claimed in your materials, is that it opens up a wider array of materials. Is that just because, as you said before, there are some materials that don't have solvents developed for them?
Yeah, that's right. It's easier to make materials that are compatible with an all dry process. If you never have to use solvents, a lot of things can be used, a lot of different polymers and even some of the active materials into the cell. They don't like solvents, and if you never need to use them, then it allows us to use a wider variety of materials.
So right now, what you're selling to people is, here's a way to make the kinds of batteries that we're familiar with, right? Like if you can go to an LFP manufacturer and say, here's machines that can produce LFP for you. But theoretically, because this opens up a wider array of materials, not only binders, but as you say, maybe even different active materials, can you see the dry process being used as like a research tool for developing new chemistries?
Absolutely. That's exactly right. Once this technology is introduced, the manufacturers are going to be able to then develop new materials for batteries or even new battery types and structures.
Right. That's kind of what I'm trying to get at. So one of the things you say is that the wet process, all you can get from the wet process is a uniform layer, basically, which means that the layer is the same thickness and density throughout. One of the things it says in your materials is that with dry printing, you can do layers that have different materials at different parts of the layer, different densities at different parts of the layer. Talk a little bit about that. Like what would be the function of that? What could you get out of that?
Right. Yeah. Batteries, they're very complicated. They have a lot of things going on in them. Lithium is moving around from one electrode to the other. The electricity, the electrons have to get in and out of the electrodes. And so there's a lot happening almost in the same space. It's almost like parts of the body. We have blood vessels that move blood around to all the tissues. In a battery, it has to move lithium, usually a liquid electrolyte, between the electrodes. But the current manufacturing can't make these complicated capillary networks inside of an electrode. Printing can. Printing has the ability to do things on the macro scale to make different shapes and sizes of electrodes and batteries. But on the micro scale, we can also put things in like channels, little networks that can actually allow the electrolyte to penetrate more easily deep into an electrode.
Oh, interesting.
So that we can have a battery then that can work maybe at much higher power, right? We can get the lithium in and out much more easily. Dry has that advantage. It does allow the electrolyte to penetrate better within the network. And then by embedding these things like capillaries within the electrode, we can even increase the power. The industry has known about this for many years, decades even, but there's never been a manufacturing technology that could make it real.
Well, I meant to ask that earlier. Like, is there a particular technological development that has made this possible, or is this just engineers getting incrementally better and better over decades, or is there something that happened that made this possible now when it wasn't a decade ago, when people, as you say, knew about this and were thinking about it? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who change majors or careers after hearing episodes of Volts. People using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. Is there a particular technological development that has made this possible, or is this just engineers getting incrementally better and better over decades, or is there something that happened that made this possible now when it wasn't a decade ago, when people, as you say, knew about this and were thinking about it?
Interesting question, actually. I think that it's really just the time is right. There has been enough development in adjacent industries like 3D printing or even document printing that have developed and matured. And it's taken time for the battery industry to recognize that, hey, people can make these other parts using these very interesting technologies. Could we apply that to battery? Batteries are a little challenging. The margins in the battery business are not very high. And so the industry is pretty conservative, and they really are demanding that any new technology be really proven, put through its paces before they're willing to take risks, because it can be dangerous.
Well, this has always been the problem for businesses trying to challenge in this industry, is that you have a incredibly well-developed target you're trying to shoot for that's been around a long time, it's very well honed, and it's a receding target because those kinds of batteries are getting better and better. So you have to prove that you can be as good or better before making any money, which is like a very difficult thing for businesses to do. It's a real tricky dance to try to be scaling up almost before people trust your product.
Yeah, it does happen. I think it's taken a little longer in the battery industry, but it is happening.
Yeah. So just to sort of recap what we were just talking about, at the micro level, at the microscopic level, dry printing enables a sort of variation and sophistication within these layers in a way that the wet process doesn't, which again, like could theoretically be used as a research tool to improve performance, as you say, to improve power and all this. The thing I keep returning to is that right now the dry process is just being used to replicate what the wet process is doing, but it does open up channels for research and improvement. One of these is at the microscopic level. As you say, at the layer level, you can actually do variations. The other, as you mentioned briefly in passing, is at the macro level, and I'm also very fascinated by this. You could print a battery in any shape, theoretically, like any macro shape that you can program, you could print a battery electrode in that shape. Is there any is it just the sky's the limit on that?
Yeah, essentially, you can think of 3D batteries kind of like 2.5D, that they're made by layers, like they almost have to be because of the nature of the battery. But those layers can be built up layer to layer in different shapes. So the fundamental shape might be a circle. It might be something that fits really well within maybe a virtual reality headset, or maybe even in a vehicle or a drone.
Well, I kept thinking about bicycle batteries. They have a very sort of unique form factor, a very unique shape.
Right.
So you could theoretically just print a battery electrode that is that shape, so it just sits right in that casing perfectly, right? Is that the idea?
That's the idea, right? Take advantage of whatever space is available for any given application. Some applications, rectangles, great. But many applications is limited, right? It might need to be shaped in order to take advantage of it. A lot of consumer applications are like that. Aerospace is the same.
Yeah, so I was wondering, returning again to the theme, it's possible that with this advance, with dry printing, you could get batteries into spaces that it has been difficult to put batteries heretofore, right? Because you can just print them in any shape, basically. Is this going to see batteries getting squeezed into places they haven't been before?
Yes, it will actually. And even applications that you might not think of, like cars. Vehicles often have a little bit of challenge taking advantage of the space available to them. By shaping the cells, you could increase the capacity of a vehicle 10%, maybe
Right.
15% by shaping them and putting them in the locations that you want.
Right. You could squeeze them into any little corner or any little extra space if you can print whatever shape you want. And you said theoretically, you could print not just the electrodes, but whole batteries. So theoretically, you could end up printing, I could build a machine that needs a battery of a very bespoke, specific shape and capacity. And then I could just send that order to you and you could just program it into the 3D printer and print a battery of that exact shape and capacity. Is that the vision of the future here?
Yeah, that capability is something I think everybody would love to have, to be able to print those cells. There's a lot of application for that, like batteries for legacy equipment where people no longer make those cells. And if you need new ones, you could make that. Batteries that are printed in the field. Military applications are very big. Those markets are highly specialized. The volumes are different. And so initially, that's not the market that Sakuu is going after first.
Sure.
Right? Because the high volume markets are the ones that can really support the introduction of new technology. Ultimately, though, the market for the kind of short run custom cells, that is out there. It exists today. And we are going to be able to take a look at that as the technology matures.
Amazing. That would be really cool. I look forward to all the different. I'm trying to return to the theme over and over again, is that this manufacturing process opens up possibilities for batteries that do not currently exist in terms not only of their microscopic performance, but of their shape and function. One other straight question, because everybody's talking about data centers these days. Data centers do not only have batteries, they often also have supercapacitors for big surges of power. Is there any reason you couldn't print a supercapacitor?
No, no. The electrodes in the supercapacitor are essentially the same. The materials are a little bit different, but it's still a mixture of powders and binders held together on a current collector. So it has the same kind of requirements, and the same advantages are in place for dry process for those applications for supercapacitors compared to batteries.
Interesting. All right. In the time left, I want to turn to basically the other big, exciting Sakuu related thing, which is these composite current collectors. So I think Volt's listeners will be aware that batteries, around the sort of the edge of the batteries, you have this strip of metal, typically copper or aluminum, I think, usually meant to conduct the electricity out of the battery into whatever current collectors. Right now, they're made of metal, which means if something goes wrong with a cell and it releases a big burst of energy, the metal conducts all that energy immediately, which is how thermal runaway gets started, how fires get started. So you guys have figured out how to print current collectors that are not made of metal. Why did you do that? What are they made of? And what are you trying to get out of that? What is the promise of current collectors made not of metal, but of composites?
So batteries have a couple key performances that they have to demonstrate. They need to be able to store the charge safely and at low cost. Those are the things that really people are looking for in terms of the battery performance. And the industry has done pretty well with that, but there's always room for improvement. There are certain kinds of batteries that have a lot of safety advantage, or maybe even energy storage advantage, like they can store more energy in a smaller space. But often they're really expensive, right? They have to be fabricated with very unusual processes or materials. And this kind of battery that you mentioned, we call it a polymer current collector battery. It uses, instead of copper and aluminum, it uses a polymer composite to conduct the electricity. This kind of battery has been known for a long time. There are publications that go back 20 years or so talking about this could be a much safer battery, a cheaper battery, a lighter weight battery.
It's safer because it has higher resistance, right? It won't conduct all the power at once in the case of a fault.
That's right. If there's ever a defect or a short inside a battery, as you say, with the copper and the aluminum, the battery can discharge all its energy within about 1 second, and it will melt or ignite, right? These other cells, they can't do that. They have an internal safety feature where if they do get a defect or short, the battery fails, it still takes a few hours for the energy to dissipate, which is plenty of time to dissipate the heat. And so the batteries are inherently safer.
So can you say that if you have composite collectors, thermal runaway fires are impossible? Sort of off the table entirely?
Yeah, the main mechanism for ignition is that instant energy dissipation. Basically, it melts or blows up. And that has made that pathway blocked by the construction of the battery. There's no way for it to happen with the materials that are made. To say that a battery can't burn or fail is saying a lot, right? I mean, there probably could be, a very strange, element, but it's taken 99% of the failure mechanisms out of the way of that these batteries can fail. And as I said, it's been known for a long time, but there's never been a manufacturing process to make these. Until now. Now we have a printer that can actually put down different materials, do it in a dry process, much more like a 3D printer, right? And that's what's required to make these kind of batteries.
What is in there that is conducting the energy?
Typically, it's the same kind of materials that are used in electrodes today. They're usually some kind of carbon black, something that conducts electricity well enough, but it's still stable within the battery. So it's not really a new material. It's the ability to print all of these different materials at the same time into the same electrode or cell. That's been the main limitation why there's been no commercialization of these kinds of batteries. And it's printing that enables that. And so now that we are introducing this printing technology, that's why we're getting people excited about these kinds of new batteries, safer batteries, lighter weight batteries that use known materials, but in a different process that actually enables these things to be mass produced.
And those materials are cheaper than the metal? Like you're reducing costs also by replacing the metal?
Absolutely, right. As I mentioned before, there are a lot of advanced technologies for batteries, but typically what they do is they turn a $100 battery into a $1,000 battery, right, to make it a little bit better. And that's not acceptable. Nobody will accept that in any application. But the materials that we're using, carbon black, polyethylene, they're incredibly inexpensive and much cheaper than the copper and aluminum that they're replacing.
One of the other things I saw in the video where, there's a video where you have one of these cells with no metal composite collector. It really is it just looks like a tiny little flat rectangle. It looks almost like a Ziploc bag full of some black substance, but it's very modest. But one of the things you said on that video also is that you don't need housing for the cell. Why is that?
So you can think of those as kind of like really large coin cells. So each of those pouches, those layers, they're very, very thin. They are essentially a complete battery. And when they're put into a pack, they can be stacked up like playing cards. And so they can be integrated without using tabs or other kinds of connections.
So just the contact from one to the next is what's conducting. So you don't need extra equipment to sort of hold them together.
Right. They're each individually sealed cells. And so they don't have to have any secondary container. Often they will. There'll be like a shrink wrap or something like that holding them together. But it's not required. They can just be stacked together because each of them is a fully functioning battery.
That's wild. So if you had just had a bunch of those laying around, you could literally just throw together a battery of a particular size just by stacking a particular number of these. Like if I literally just stack them on the floor of my garage, whatever, 20 of them on top of one another. That's a battery right there. That's
Yeah, exactly.
I can hook that up to something and run something on that.
Exactly right. Yes.
That's absolutely wild. Do you think that now that is possible and other manufacturers see that is possible, do you think that in the fullness of time, the industry is going to shift from metal current collectors to composites overall?
I do. Usually, these kinds of breakthrough technologies are limited because there's always a trade off. In some aspects, the product gets better, but in others, there's a trade off. Maybe there's something that's not quite as good.
Batteries are full of trade offs.
But the technologies where things are just better. Look at LED lighting. That's a great example.
Yeah, right,
Once
right.
the quality of the illumination and the cost became better in all aspects, there was no limitation anymore. It was just time, and things accelerated and they took over. In battery world, it's the same. By using these kinds of polymeric materials that are lighter weight, they're cheaper, but they work as well and they're safer than the cells today. The only thing that's been holding it back is the lack of manufacturing technology. Now that that's being introduced, there's nothing that's going to stop it from being able to take over as many applications as people have the imagination to consider.
Getting back to Saku's business, I'm sort of curious, like you say, if you can show that this works, other people are going to herd into this, as you say, because it's cheaper and better if you can get it to work. What is your sort of moat? What is your IP? What have you figured out that has put you ahead here? Is it the mixing of the dry materials? Is it the actual physical printing itself? You've improved printing? Or is it what's your sort of business sauce that you've got going for you?
Yeah, it's twofold. The formulation of the material is the key, the initial key. And that's where Sakuu started. Even before we had a printer, we were developing the dry powders that we can use in the printer.
That's materials science. That's just chemists in the lab.
Yeah, material science and electrochemistry.
Yeah, my favorites.
And then the second is the printer itself, because once we have the dry materials, can you put that down where you want it precisely, reliably, and at high speed?
Got it. And so with this machine you've made, you can now produce electrodes in batteries that are cheaper and safer, allegedly, and a wide variety of materials, and theoretically even some new kind of batteries that I've never seen before. Is the premise of the business that you're selling the printers, or are you also going to be selling the electrodes and the batteries that you come up with?
So we're enabling our customers to do the innovation, right? So we're developing the manufacturing equipment and the process and material technology around that. And we do have some ideas about 3D structures in the batteries, shapes, sizes, and new battery architectures that our technology enables. Ultimately, our customers are going to go way beyond that. They're going to take this new capability to print different materials, and they're going to be able to do even more than that. So we are enabling them. So we are selling the equipment and licensing the technology that around it to our customers, enabling them to make cheaper, better batteries. Some of them are going to be the things that we've been talking about here, and some of them are going to be things that we haven't even thought of at this point.
Yeah, I mean, this was sort of me getting to my final question. This is what I was trying to sort of figure out. But the idea here is that eventually these printers will be relatively easy to access. They'll be numerous, they'll be around. A lot of people, different people will have access to them, which means like any sort of like chemistry department in a college or university lab can just spend all its time fiddling with dry materials to sort of perfect and make new kinds of batteries, right? Like this is going to be a tool, an incredible tool for innovation.
I think the whole technology is really exciting because it enables people to think in different ways and integrate materials and ideas that they haven't really been able to do before because the manufacturing of batteries was very inflexible. They had to be a particular material set and form factors and things like that. I'm constantly amazed by the innovation of people when they get new tools and new capabilities about where it can go.
Yeah, that's what's most exciting to me about this is just putting these in the hands of different people. Like who knows what people are going to come up with. And one other question about the like 3D printers are like weird. They just seem a little bit like magic to me. So I'm constantly trying to figure out what are the limits of their seemingly godlike powers. But like a 3D printer theoretically is material agnostic. So a 3D printer that could print an electrode could theoretically also print, as you say, the casing, could theoretically print the whole battery, could theoretically print the whole thing in which the battery is integrated. So in other words, like, do you envision batteries being much more deeply integrated into materials with this capability? You know what I mean? Like you could sort of worm them. You could make them like a part, like I think for the bike battery, for instance, like you could make it a part of the column itself rather than something attached to the column. You know what I mean? Like you just print a bike tube with a battery in it. Like you could put batteries anywhere with this is what I'm saying.
Right. I think this is getting into the vision that people have for 3D printing in general. How far can 3D printing penetrate into traditional manufacturing process?
I'm very curious, but do you have any thoughts about that after working with these things now for over 5 years? Do you have any sense of the limits of like what parts of manufacturing could they not do? Like what do you think are the limits of 3D printers?
I think it's fully within the realms of possibility that those kinds of things could be printed, like a battery that is integrated into the drop tube on a bicycle or other applications like that. Those are fully within the realm of what could be achieved in not too distant future. Ultimately, though, cost is a big driver in a lot of applications. It's one of the and performance, and it's one of the reasons we don't see very many 3D printed bicycles today, for example, right? Mm. And those trade-offs or those different restrictions and considerations have to be all taken into account. You know, what's going to be the best way to make an integrated device? Is it going to use these technologies or not? Time will tell.
Mm-hmm. But you think for batteries, this is a clear winner. The dry process is the clear winner, you think?
Anything that can make better batteries cheaper is going to win. And the printing technology does that. It actually makes better batteries cheaper. And the more that we play with it, the better they get and the cheaper it gets. And so I don't see any reason why this technology isn't going to have a huge impact in the battery business.
Amazing. So cool. Well, Karl, this has been a delight. I love hearing about things like this. Thank you so much for coming on and walking us through it.
Happy to do it.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.